Okay, so as we get started with this next lesson here, you know the drill by now. Set up the problem of the day. We have an error analysis problem. Once again, you should know by now to pause the video and solve it in your notes before you move on to the actual lesson. Okay, so 1.5 is called Use Problem Solving Strategies and Models. So the first term we actually take a look at is called a verbal model. It's called the word equation written before you begin the mathematical equation. So really, anytime you see a word problem, you really should see how it's written out before you write what that translates to in math. So there's three major strategies we're going to take a look at today. Number one is a formula. First thing you want to look for when you read a problem is there a formula that I know that I could use? And we saw formulas in the last lesson, right? The next strategy we're going to take a look at is look for a pattern. All right, math has a lot of patterns that could be beneficial to some word problems we'll look at. And the third type is going to be draw a diagram. We're going to take a look at an example of each, all right? And why we're looking at math this way, I know a lot of times you see a word problem, you freeze and you don't know where to go with it, and most of the time what do I see as a teacher? It gets skipped. Well, we don't want that to happen. So we're going to take a look at three strategies that you could use all throughout the year and all throughout math, or any class for that matter, as how can that help me? All right, so let's look at example one. It says the driving distance between Boston, Massachusetts and Cleveland, Ohio is about 660 miles. If you drive this trip in a total of 12 and a half hours, what is your average speed? So we have three strategies that we can use. And it probably isn't going to come as a surprise, but we're going to start with the formula. Hopefully you remember the formula that we just talked about, no, actually the last lesson. But if I'm talking about distance, so sometimes with the word problem, I like to underline things. With distance, we have hours, and we want speed. Hopefully that brings to mind the formula D equals RT. Distance equals rate times time from our previous lesson. All right. So if you look here, we're looking for speed or the rate. So if you remember from the last lesson, let's already rearrange the formula. Because remember I said in the last lesson, sometimes it's easier to rearrange them first before you actually go about solving. So if we want speed or rate by itself, we're going to divide t by both sides. And we're going to use rate equals distance divided by time. And then all we have to do, with it already rearranged, is plug in our information. So the distance is 660 miles. Over 12 and a half hours. And when we divide those, we're going to get rate equals 52.8. It's going to be decimal, 52.8. It's miles per hour. And I think we know by now miles per hour can be abbreviated to mph. It's a common way we see it. You might be wondering, how does she know it's miles per hour? The distance is miles, the denominator is hours, and if we divide, we call it per, so miles per hour. So there's our answer. So the first thing you're going to take a look at when you have a word problem is there a formula I have that I already know that can help me solve this? Okay? Example 2. The table shows the number of seats in each of the first 4 rows in the auditorium. The remaining 10 rows follow the same pattern. And it says find the number of seats in the last row, which is row 14 of the auditorium. Now, obviously, if you haven't noticed yet, we're going in order. We're going to take a look at the second strategy, which is look for a pattern. So I want to look at what goes on between each of these. So as I continue one row up, you'll notice, and I usually like to draw on my charts or tables here, what do? I add 2 seats, and I add 2 seats to get from here, and so on. So we see the pattern that to get to the next row, we add more seats to it. Now, one thing I'm going to have to add, and I'm going to draw a little line here. There's going to be 2 numbers we use. Obviously, 2 is going to come into play, but we have to see where it starts. We always want to know when the row is 0, or we call this x and y. Sometimes I like to think of it as equation of a line. Now, I know for this problem, 0 rows does not make sense, but you always want to see what happens when x is 0. All right, so logically it doesn't make sense, but we know if we're adding 2 each time, all right, well then if this is 0, the y or the seats would be 10. So the number here, we're going to write it in y equals mx plus b form. The number that we increase each time, which is plus 2, will be the number in front of the x, so 2x. And whenever x is 0, that's our y-intercept, or b, which is 10. So I like to think of it as if I was graphing a line. The 10 is the y-intercept. I go up 10, plot the point, and my slope is 2, or 2 or 1. So from 10, I go up 2, right 1, up 2, right 1, and so on. So here's my equation. All right? Now, the next part, if we look at it, is find the number of seats in the last row, 14, the auditorium. Well, the row is x, so let's plug in 14 and see from coming up with our equation, all right, well, how many seats do we have? And if we plug it in here and solve, you're going to get the number 38. That's seats. That's our answer. So there's really 2 parts to it. You're going to work on, from a pattern, come up with an equation, this part here. You're also going to tell me like an answer at the end. All right, so we took a look at formula strategy, look for a pattern strategy. We have one last strategy, no surprise here, and that's going to be called draw a diagram. A lot of times in math, and I know this from example as well, if I have a lot of information going on, I like to draw a diagram and sort of figure out where I'm going with this. So I actually already have the picture started for us here. So I'm going to read along with you for the last one. So make sure you have this picture drawn or you have the notes printed off. You're hanging 3 pictures on a wall in your home that is 16 feet wide. So the purple background signifies the wall, and the neon green rectangles, even though it's not really fancy here, signifies the pictures you're hanging. So we have 3 of them here. All right. The wall is 16 feet. So from here, what I'm going to do, I'm going to probably write down here, is we're talking about the width. So 16 feet. And that goes all the way across. So once we have our diagram, we're going to start to label stuff here. So here's our 16 feet. I put a little slash mark for feet. The widths of the 3 pictures are 2 feet, 3 feet, and 4 feet. All right. So we'll go with the smaller one here. This will be 2 feet. And it goes from here to here. 3 feet. Let's do the bigger next size up here. Slash mark for feet. All right. And 4 feet. All right. So make sure you're labeling in on the picture here. Okay. Now, let's keep reading. You want the space between the pictures to be the same if the spaces to the left and right of the group of pictures to each be 6 inches more than the space between the adjacent pictures. All right. So between the posters or pictures, we want the same amount. So I'm going to call it x because we don't know what that number is. We want it to make it look even, right? This is going to be x. And you know, actually, this is a really practical application because I know even in my house, when I hang pictures, I sort of want them to be symmetric to the eye, right? So it's a pretty believable problem. At the end, it says, though, we want it 6 inches more. So we're going to write x plus 0.5 on each. And I know I wrote really, really big here. That's just this piece here. We're going to do it over here too. X plus 0.5. Fix the x there. All right. You might be saying, why did she pick 0.5? And I'm getting there. Give me 1 second. And that's just the space here. I wrote a little too big. So this is the x plus 0.5. All right, well, it's telling us 6 inches more. Now be careful, because what is everything else measured in? 16 feet, 4 feet, 3 feet, 2 feet. So it's half a foot or 6 inches. So I had to make sure I did that conversion there. Okay? Now, it says, how should you position the pictures? All right, are we ready to solve? The hardest part is drawing the picture and setting this up. Okay, now give me a second here. What I'm going to do is delete the problem, so I have all this room to write. Okay. Do you see how I have everything for the width? I can actually start writing an equation. I think this one, I'm going to be able to type it out. This might be pretty easy. So do you see how we have x plus 0.5, 4, x3, x2, x plus 0.5? We're going to add them all up. So we write x plus 0.5 plus 4 plus x plus 3 plus x plus 2 plus x plus 0.5. I'm simply adding all the widths across, all right? Now, what is that going to equal? What we have all the way at the bottom, which is 16, all right? So it's 16 feet across. Now, all is that we have a matter of is an equation here. So I'm going to sort of simplify everything and combine like terms here. So if I add all the x's together, I get 4x plus, if I add 0.5, 4, 3, 2, 0.5, I'm going to get the number 9. And that's going to equal 16. And now I have just an equation to solve. I'm going to get 4x equals, oh, hold on 1 second, back up for a second. That's 10. Sorry, guys. When I add everything up, now I subtract 10 from both sides, so transpose the 10 over as a negative 10. 16 minus 10 is 6. And when we divide, we get 1.5 as our answer. So if you want to go back in, we can actually say, see if I could do this here. This is 1.5. So you would just sort of explain what x is and what happens. This is 1.5 here, feet here. All right, so is this. So if we're evaluating for x. And on the edges, we do what? 1.5 plus 0.5, which is 2. And there's your positioning. Okay. So that brings us to the close of our lesson. Homework, you know the drill by now. Do the problem of the day for 1. Then answer problems 2, 3, and 4. And we will talk about it in class.